Ohio. November 1942. It's after midnight, and the entire building is supposed to be dark, but one window is still glowing inside a small machine shop north of Dayton. The snow outside hasn't started falling yet, but the air smells like it will. Inside there is a man who hasn't gone home in 19 hours. His name is Russell Rusty Carter, a name that will never appear in any official post-war book, any victory parade, any presidential citation or any magazine. And yet what is happening inside this machine shop tonight is America's war explained in one man. There is a stack of drafts and graph paper scattered everywhere on his bench. Almost every sheet has the same shape, two circles side by side like two clocks drawn next to each other. The twin side-by-side propeller concept. It looked so clean in his mind 6 months ago. It looked like a geometric cheat code. It looked like the kind of idea that only appears one time in your life, and then it either changes the world or it dies in the trash can. Rusty believed it was the former. Then the wind tunnel data said the opposite. Every test, every angle, every tweak, all failure, pure drag, interference catastrophe. In the last meeting, a senior aerodynamicist laughed at him to his face. Rusty, you're a good mechanic. Stop playing scientist. Tonight Rusty sits alone. He knows tomorrow morning he will have to walk into that same building full of men who already consider his idea dead. He knows if he lets that happen his life will become like every other machinist in Ohio. Clock in, clock out, punch metal, do what you're told, don't try to think. He refuses. He looks at the two circles again. He draws them again. He draws arrows of rotation. He sees the interference zone between them. And then he does something that is so stupid it becomes brilliant. He draws one circle on top of the other. He takes the two circles and slams them into a single axis. There is no fanfare. No swelling music. No eureka scream. Just a pencil stroke that changes everything. Contra-rotation. Coaxial drive. Two propellers on the same axis spinning opposite each other. Torque cancellation. Higher effective blade loading. No side drag war between two separate discs. The limitations that were killing the side-by-side idea, gone instantly, because the geometry has been flipped inside out. Rusty stares at the line. His heart rate climbs. It's like watching a locked safe crack open. He doesn't even stand up. He just sits there and keeps drawing. He sketches rough blade angles. He scribbles torque math. He grabs data from the failed sheets and plugs them into the new geometry. The numbers don't merely look better. They look like the doorway to another world. He sees an engine's full power truly delivered, not wasted encountering its own torque. He sees speed that no single prop airplane has ever touched. He sees 470 miles per hour becoming physically plausible. He sees the future. But nobody else will believe him tomorrow morning because nobody in that building believes in the future unless it already exists. This is the invisible part of American history. War is decided by production, yes. But production is downstream of thinking. And thinking begins with humiliation, with being laughed at, with people telling you you're not allowed to have an idea because your job title doesn't include the word engineer. Rusty Carter is the reason America wins wars. Not because his name is famous, but because his culture allows the machinist to challenge the PhD. Because America in 1942 was the one place on Earth where a guy like Rusty could walk into a room full of credentialed experts, drop a new geometry on the table, and force them to confront the possibility they have been wrong this whole time. This is how a nation becomes unstoppable, not through arrogance, but through the brutal willingness to break its own assumptions faster than the enemy can break theirs. In a few months, ideas like Rusty's will be crossing the Atlantic, traded in technical packets between US and UK labs. In a year, the British will bolt monstrous Griffin engines onto Spitfires and start thinking about the unthinkable. Can a piston fighter touch 470 miles per hour? That hypothetical only exists because of nights like this. One man. One failed idea. One moment of not surrendering to mockery. Rusty Carter leans back in his chair, exhausted, his eyes red, his pencil nearly broken. He has no idea if any colonel, any procurement board, any airplane manufacturer will ever greenlight this. But tonight is not about approval. Tonight is about the truth hidden in the numbers. America wins wars with ideas. And sometimes the idea is born at 1:37 a.m. on a freezing November night in Ohio, drawn by a man nobody will ever remember, sitting alone in a machine shop, refusing to give up. To understand why this night matters, you have to understand where Rusty is standing in the timeline of the world. 1942 is the year the United States stops being a country and becomes a factory. This is not poetic. It is literal. Every hour, every day, every week, the nation converts its entire peacetime bloodstream into industrial throughput. Government people call it mobilization. But the men inside it don't use that word. They call it work. They clock into it. They bleed into it. Ohio is one of the primary hearts of this machine. People in the coast think innovation means MIT lecture halls or California eccentric garage inventors. But in 1942, the most important intellectual property in America is not on the coasts. It is in the Midwest, inside shops that smell like coolant, kerosene, hydraulic fluid, and wet steel. This is where the tooling for aviation lives. This is where the cutting tolerances for the future are forged. This is where the United States is quietly building the capability to scale any idea that works into tens of thousands. Rusty lives inside the real America of 1942. The America where a machinist can walk into a diner after midnight and every booth is filled with machinists, draftsmen, women from the night shift making bomber parts at Wright Field, tool makers, riveters, welders, and the conversation at the counter is not politics, not ideology, not even the war per se, but throughput. Your jig is binding on the last third of travel? You should stone that bearing surface again. Try a different polishing compound on the last pass. This entire civilization is learning precision at scale. And in parallel, America is building the thing that all modern aerospace depends on forever after 1942, the scientific method as an applied industrial pipeline. Because wind tunnels are not just technical toys. Wind tunnels are where ideas live or die. They are the courtroom. The geometry Rusty is struggling with, the twin side-by-side concept, has already been through that courtroom and the verdict was guilty. It failed. It wasted energy. It was a pretty shape that got murdered by fluid dynamics. A weaker culture would bury the man who proposed it. But here is what makes the 1942 U.S. ecosystem unique on Earth. Failure is not a verdict, it is a pivot. That is the American difference. The Soviets punish their engineers. The Japanese militarize theirs and then rigidify their doctrine. The Germans bury ideas that don't instantly perform because their hierarchy suffocates the experiment. But America, especially Midwestern America, is a frictionless marketplace of tinkering. Rusty's shop culture is not gentle. Yes, they laughed at him. Yes, they mocked. But the difference is, they laugh and mock and then they still let him keep a bench. They don't exile him. He still gets access to the machines. He still gets access to the draft tables. He still gets to resubmit. That is the secret. American innovation works because America lets the guy who failed come back with a new idea tomorrow, instead of shoving him into administrative prison. And the timing is perfect. Because in 1942, we are inventing something else. The American-British Technical Data Pipeline. The U.S. is already shipping airframe analysis notes, powerplant curves, wing efficiency studies, turbosupercharger optimization memos, and the British are sending back their own research. There is a new normalization happening, a common scientific language of the free world. So when Rusty redraws his failed twin disc into a single coaxial contra-rotating disc, the possibility space instantly expands beyond this building, beyond Ohio, beyond the United States. An idea that works in Ohio can, within months, be sitting on a bench at Farnborough in England. And maybe, if some British madman sees the same thing Rusty sees, that contra-rotation unlocks power that single props throw away, then the idea could leap species. It could get bolted to a Griffin. It could push a Spitfire into the zone that until now is science fiction. This is the strategic context. Rusty is not just drawing a new propeller layout. He is injecting a mutation into the global Allied brain. And this war, unlike any war before, will be won by the side whose mutations compound faster. Everything Rusty does tonight is invisible. But invisibility does not mean irrelevance. In 1942 America, the future is being carved by hands like Rusty's, in small shops at impossible hours, powered not by glory but by stubborn belief that you are allowed to have ideas even if the world tells you that you shouldn't. Rusty Carter is not a genius. He would hate that word. He would call himself a good hand. He was born outside Dayton in a house that never had enough insulation. His father worked at a foundry. His mother cleaned offices at a law firm downtown. Nobody in that family owned a library. Nobody in that family ever sat at a draft board. But Rusty's father had a habit of bringing home broken things from the shop. Cracked housings, damaged fixtures, bent spindles. And Rusty learned early that there is no such thing as scrap. There are only parts that are waiting for the right mind to see a path back to usefulness. That is his psychological operating system. Everything can be saved if you look at it the right way. He never went to university. He went to the tools. His original plan was to be a mill operator. He wanted the feeling of steel under feet. He wanted the feedback loop of tool chatter and sound pitch and surface finish telling you if you are doing it right. But machining is a gateway drug. 1 year you are cutting aluminum webs for somebody else's drawings. 2 years later you understand the drawings. 4 years later you start drawing your own. The lines on the paper are just the shadows of the cuts you intend to make. While other men collect cigars or guns, Rusty collects failed ideas. He clips diagrams from magazines of wild French pushers, of weird British tractor hybrids, of Italian counter-rotated coaxial floatplane prototypes. He files them. He studies them. He studies the failures as if they are sacred scripture. He is not trying to be first. He is trying to be the guy who understands why everyone else failed so he does not step into the exact same traps. He has a defect. The kind that looks like a moral failure to the small-minded. He gets obsessed. He walks into the shop after midnight even when he is not on shift. He burns lamp hours like other men burn cigarettes. He will ruin a weekend because he cannot stop thinking about a blade-tip vortex he saw in his peripheral imagination. At his worst moments he is almost possessed. But the possession is not random. It is disciplined. It is directed. And it is always toward the promise of extracting more power from the same cubic inch of displacement. He is patriotic but not in a flag-waving way. He believes America is special because America lets men like him exist. He knows he would be crushed in Germany. He would be exploited in Japan. He would be ignored in Britain. But in America, the shop foreman will look at him sideways, call him crazy, and then say the sentence that is the most American sentence ever invented. Go ahead and try it. That is all Rusty ever needs. He keeps a notebook. Not a leather journal. A cheap dime store ledger. Every few pages there is a line. And under the line a new title. These are not project names. These are questions. Can you neutralize gyroscopic precession without losing disk authority? Is there a torque symmetry cascade at dual tip speed? Can contra-rotation run at negative interference if disk spacing equals half chord? These are the questions that shape the future. He is 28 years old. He has no degree. He has never been to Europe. He has never even seen a Spitfire in person. But he is about to change the way the Allies think about propellers. He is about to put his fingerprints, indirectly, on the most iconic fighter shape of the free world. And the thing that will make this transformation possible is not raw IQ. It is the moral courage to look at the entire world telling you that you are wrong, that your idea has been tried, that your geometry is dead, and then quietly saying, maybe you all looked at it from the wrong direction. That is the man tonight, bent over his drafting bench, drawing a coaxial propeller stack that nobody asked for, and that nobody believes will work. The Americans and the British share the same nightmare in 1942. Horsepower is now hitting the ceiling. We can keep raising boost. We can keep raising compression. We can keep adding intercooler capacity. We can keep squeezing every cubic inch of displacement. We can keep pushing the Merlin and the Allison toward the edge of reliability. But you eventually slam into the same wall. The propeller turns the power into waste. Every extra horsepower after a certain threshold becomes heat and swirl and drag. You can raise the power plant curve another 50 horsepower on the dyno and the airplane barely goes any faster. This is the place where the war becomes a mathematics of diminishing return. The British already feel the edges of this trap. They have the Spitfire, the most beautiful aerodynamic sculpture of the Allied world. And they know the shape has more speed left in it. The airframe can take more. The wing still has more to give. The structure can carry more load and maintain coherence in high-energy dive and pull-out. But the bottleneck is not the wing, not the cooling pack, not the pilot. It is the propeller disc. It is the invisible black circle in front of the airplane that decides how much of that combustion becomes acceleration versus how much becomes empty air vibration. The Germans have a solution. They pour their energy into direct injection and exotic supercharger topology. They push the envelope through the engine itself. But the Allies are fighting a different war. We need throughput. We need quantity. We need reliability. We need a system that can be industrialized. This is where Rusty's problem becomes the Allies' problem, and the Allies' problem becomes Rusty's problem. He knows the theory. He knows why side-by-side twin props failed. The interference field is horrific. The wakes collide and amplify drag. The blade tip vortices become pathological. The entire energy transfer becomes turbulent trash. Side-by-side is a graveyard. But coaxial is different. Contra-rotation cancels torque. Contra-rotation neutralizes precession. Contra-rotation lets you reclaim bite at higher power density. But here is the monster nobody wants to face. Contra-rotation also creates a control problem. You are adding a second gyroscope ahead of the airplane's reference center. Both are spinning. Both are storing angular momentum. In a turn, those gyros want to impose their own truth on the airframe. The airplane becomes a negotiation between aerodynamic intention and spinning mass stubbornness. And in 1942, the available control surfaces are already working near the edges of their authority envelopes. So Rusty is not just trying to draw a cute weird propeller. He is trying to solve the most complicated control moment problem in piston aviation. He needs more bite with less torque penalty and no catastrophic control penalty. The men in the shop laugh because they think it is impossible. And to be fair, Rusty has failed at this geometry twice already. He tried twin discs in parallel, a disaster. He tried twin discs with slight stagger, another disaster. He tried differential pitch on conventional side-by-side, and learned nothing except how fast a man can burn through aluminum when his brain is racing ahead of his hand. But tonight is different, because he has stopped thinking like a guy who wants to get both discs to cooperate. He has begun to think like a guy who wants the discs to fight each other. Not violently, but constructively. He has an epiphany that sounds insane to anyone who has never touched real hardware. Maybe the trick is not to force the two discs to share airflow. Maybe the trick is to let them fight over it, and let the fight extract the energy. Maybe the drag that everyone sees as waste can become the raw material for thrust. Maybe the second disc can carve the chaos left by the first disc into order. This is the birth of the idea. The first disc is the artist. The second disc is the editor. And if you adjust pitch distribution across the radius of each disc, you can make the first disc produce an intentional mess, and make the second disc mine that mess for usable thrust. This is the opposite of every intuition in 1942. The entire Allied world is trying to make cleaner airflow. Rusty is trying to weaponize dirty airflow. There is a second deeper problem beneath all this. Rusty is American. And Americans are not supposed to have opinions about Spitfires. Diplomatically, the US and Britain are allies. Industrial reality, they are competitors. America is trying to prove that American mass production systems are superior. Britain is trying to prove that the old world still has the artistic touch, the taste, the cultural sophistication, to produce aerospace beauty that the new world still lacks. If you are an American Midwestern engineer in 1942, saying out loud that you might have a way to make the British Spitfire faster, is like telling the world you think you can repaint the Mona Lisa. Who do you think you are? That is the emotional wall Rusty is smashing against. He does not have political permission. He does not have institutional permission. He does not have cultural permission. He is trying to solve a problem nobody asked him to solve. He is trying to push an idea into an airplane that is not even his country's airframe. But here is where America is unique. He doesn't need permission. In America, solutions are allowed to become arguments. Arguments are allowed to become prototypes. Prototypes are allowed to pressure the world. If the idea works, the idea will find a path. That is the most American principle on earth. The idea decides the path, not the hierarchy. Tonight, Rusty is not trying to draw a propeller. He is trying to escape the prison of consensus. He is trying to rescue the free world from the horsepower wall. He is trying to prove that an American outlier working on the night shift in Ohio can bend the aerodynamics of the British crown jewel and push it into a performance domain nobody had words for yet. 470 miles per hour in level flight. That number is not madness. That number is the hidden truth waiting behind the problem if the double disc becomes more than a joke. Ohio, November 1942. The snow hasn't fallen yet, but the chill has crept inside every corner of the small machine shop north of Dayton. Outside, the streets are quiet, almost peaceful, but inside the shop, one man refuses to rest. Rusty, Carter sits hunched over a drafting table, a single flickering bulb above him casting shadows on scattered sheets of graph paper. The silence is absolute, except for the scratch of his pencil against the page. Rusty's idea is simple and yet insane. 2 propellers. Side by side. Twin discs spinning independently. Everyone calls it stupid. Engineers in Dayton's big factories have laughed at it. Aerodynamicists in Cleveland have rolled their eyes. The men in his own shop have called it impossible. And yet, Rusty believes, not because he has a degree or a title but because he understands steel, airflow, and the stubborn behavior of spinning air, that this stupid configuration could be America's key to pushing piston-powered aircraft beyond what anyone thought physically possible. He redraws the discs again and again. Every line, every circle, every arc is scrutinized with the precision of a man who has no margin for error. Every night, he repeats the calculations, refines the sketches, and questions assumptions the textbooks have been teaching for decades. Drag is a monster. Torque is a monster. Turbulence is a monster. Every problem is real. Every failure so far is a warning. But Rusty is driven by a singular conviction. The solution exists somewhere in the numbers, in the geometry, in the blades themselves. And then something clicks. A pencil stroke. A simple decision. Stack the discs along a single axis instead of side by side. Spin them in opposite directions. Contra-rotation. Torque cancellation. Higher usable blade loading. The chaos of the first disc becomes fuel for the second. The problem is no longer a problem, it is raw material. The implications are enormous. In theory, this could allow any airframe, even something as iconic as the Spitfire, to extract full engine power without being punished by drag or torque. A 470 miles per hour piston fighter is suddenly within reach. Rusty doesn't know if it will work in practice, or if the British will even pay attention, but he sees it. He can see it in the numbers, in the curves, in the subtle interactions of the air and the metal. Yet the greatest challenge is not technical. It is cultural. Rusty is an American Midwestern machinist, uncredentialed, unknown, and unproven. In Germany or Japan he would be invisible, ignored, or worse. In Britain he is just an outsider. In America he has the peculiar privilege of freedom. The freedom to fail, to try, to submit an idea without permission. It is this culture, this quietly radical aspect of American society in 1942, that allows him to take the impossible seriously. Tonight, Rusty sits alone, exhausted, eyes bloodshot, pencil nearly worn to a stub. Outside, the wind carries the scent of snow and cold. Inside, the smell is oil, metal, and possibility. The world cannot yet see what he sees. The generals, the factory supervisors, the pilots, even the aeronautical theorists, they will dismiss this idea until the numbers force their attention. And yet, Rusty's quiet determination is the kind of force that reshapes history. Because America does not win wars only with weapons. America wins wars with people like Rusty Carter. Stubborn, curious, unafraid to challenge authority, and willing to experiment in the face of ridicule. Tonight is the first night of the story that will eventually ripple across continents. It is the night when an idea dismissed as stupid begins the transformation of air combat. The night when a machinist in Ohio whispers to himself, "If it works, use it," not knowing if anyone ever will. This is not a story of fame. Rusty Carter's name will not appear in headlines. He will not walk in parades. But his idea, born in silence, nurtured in the hum of machines and the flicker of a single bulb, is about to enter the bloodstream of the Allied war effort, quietly bending the trajectory of history. Because America's secret weapon is never the engine, the wing, or even the airframe. It is the mind allowed to think freely, to fail boldly, and to persist relentlessly. And tonight, that mind belongs to one man, Russell "Rusty" Carter. To understand why Russell Carter's lone night in Ohio matters, we have to see the world as it was in 1942. The United States had transformed virtually overnight from a peacetime nation into a colossal war machine. Factories that once produced washing machines and tractors now churned out bombers, fighters, engines, and propellers at an industrial pace unmatched anywhere on the planet. Every small town with a machine shop, every Midwest workshop, every humble metal lathe was a critical node in the largest logistical and technological operation humanity had ever seen. Dayton, Ohio, was part of the beating heart of this network. Its streets were lined with small manufacturing facilities that fed into Wright Field and the larger aviation ecosystem of the Midwest. Here, the language was not policy or politics. It was precise and it was technical. Men and women spoke in microns, torque, pitch, and feed rate. The conversation at the diner after midnight wasn't about victories or losses overseas. It was about tolerances, tool chatter, and the way a bevel could shave fractions of a second off assembly time. This culture, obsessive, meticulous, relentless, is what allowed ideas to flourish in America in a way they could not anywhere else. Meanwhile, across the Atlantic, the British were facing their own aviation dilemma. The Spitfire, their proud fighter, was elegant, agile, and fast, but it too faced the invisible limits of physics. Its engine had room to grow, yes, but the propeller, the single rotating disc at the nose, was already the bottleneck. Any increase in engine power beyond a certain point simply produced more drag, torque problems, and wasted energy. The performance ceiling was looming, and the British could see it clearly, but lacked the industrial bandwidth or design freedom to experiment wildly. The Germans, meanwhile, had focused their energy on exotic power plants and direct injection systems, pushing engines to their limits and beyond. Their solution was impressive but fragile. It demanded precision, resources, and strict adherence to doctrine. Any deviation could lead to catastrophic failure. Japan relied on doctrinal conservatism, emphasizing repeatable designs over radical experimentation. By contrast, America had created a fertile environment for tinkering, improvisation, and calculated risk. Here, a machinist could sit for nights on end, obsessing over blade angles and interference vortices, without being fired or exiled from his craft. Failure was not fatal, it was data. Rusty Carter's shop embodied this philosophy. He faced ridicule, yes, but it was the kind of ridicule that forced refinement rather than stifling it. He had access to the machines, to raw materials, to data. He could test, iterate, and learn. The wind tunnel, the ultimate arbiter of aerodynamic truth, was nearby. It would later tell him which ideas would fly and which would crash, but at this moment, it was just a blank stage for experimentation. America's advantage in 1942 wasn't just industrial scale. It was the ecosystem that allowed the small, uncredentialed, relentless mind to challenge orthodoxy. The very structure of American innovation enabled the kind of thinking that produced breakthroughs that were invisible at first. Small tweaks that would, in a year, reach British designers and engineers, influencing aircraft development across the Allied world. This is why Carter's idea, born quietly in a Dayton workshop, had the potential to reshape the Spitfire. Not because he had the authority or fame, but because America allowed the experiment to exist at all. The idea could travel across the Atlantic through letters, technical papers, and sketches, reaching minds capable of interpreting and applying them. Within months, a British engineer in Farnborough could hold a sketch of Carter's coaxial contra-rotating design and glimpse a way to push a fighter beyond the speed limits that had seemed insurmountable. And so, while the world was embroiled in global conflict, the real battle was also being waged in workshops like Carter's. The fight was over the limits of horsepower, torque, and aerodynamics. The difference between success and failure was measured not in medals, but in persistence, insight, and the courage to pursue what others deemed impossible. In essence, 1942 America was not just a country at war. It was a living laboratory of industrial ingenuity. Ann Carter, a machinist by trade and an obsessive experimenter by nature, was positioned at the perfect confluence of talent, culture, and necessity to turn a dismissed idea into a transformative force. The backdrop then is clear. A nation operating at unprecedented speed, a global conflict demanding breakthroughs, and a culture that prized experimentation over hierarchy. In that environment, the stupid twin-propeller idea was not just feasible. It was waiting for someone bold enough to pursue it, night after night, in silence, with nothing but pencil, paper, and an unrelenting belief that the numbers could be bent. And Rusty Carter was that someone. Russell Rusty Carter is not a man who inspires awe the moment you meet him. He is not polished, not charismatic, not decorated. He is ordinary in every visible sense. Yet, beneath that ordinary exterior is an extraordinary mind, forged by years of hands-on work and a relentless curiosity that defies conventional training. Born in a modest Ohio home, Rusty grew up amid the clatter of foundries and the smell of molten metal. His father worked long hours at a local steel plant, and his mother cleaned offices downtown. There were no libraries, no mentors, no elite institutions. But there were broken things, machines, tools, small devices left abandoned or discarded. Rusty learned early that nothing was truly useless. Everything could be salvaged, fixed, or repurposed. He internalized the lesson that persistence and observation could turn failure into insight. He never attended university. His education came at the workbench, the lathe, and the drafting table. 1 year he was cutting aluminum webs. 2 years reading blueprints. 4 years designing parts. He learned to think like metal, how it bends, twists, and vibrates, and how the air interacts with it when spinning at thousands of revolutions per minute. To Rusty, the world was a series of problems waiting for hands and mind in concert to solve. Rusty's obsession with failure is almost spiritual. He collects sketches, diagrams, and prototypes from magazines and engineering journals, not because he wants to copy them but because he wants to understand why they failed. He treats failure as sacred data, each discarded experiment a lesson etched in aluminum and ink. He studies vorticity diagrams, blade tip effects, and torque anomalies as if deciphering secret codes. To him, understanding the mistakes of others is more valuable than taking credit for successes. His defect, or his gift depending on perspective, is obsession. Rusty works through nights, weekends, holidays. He burns lamp hours far beyond what the average man would consider reasonable. He follows mental threads that lead nowhere before snapping back to the solution. He will ruin sleep and social life for a single insight about airflow over a propeller blade. To outsiders he may appear fanatical. To himself he is merely faithful to the problem at hand. Rusty is patriotic in a subtle, almost mechanical way. He does not attend rallies. He does not fly flags. But he believes deeply in the principles of American innovation, the freedom to fail, to tinker, to pursue the improbable without fear of reprisal. He knows that in Germany he would be crushed by hierarchy. In Japan he would be constrained by doctrine. In Britain he would be dismissed as a foreign machinist meddling in sacred fighter designs. In America, however, he has the privilege to act, to experiment, and the only authority he answers to is the truth of the machine. He keeps a ledger, not a leather-bound journal, but a cheap dime store notebook. Inside he writes questions, not answers. Can gyroscopic precession be neutralized without losing disk authority? Is there a torque symmetry cascade at dual tip speed? Can contra-rotation function with negative interference at half-chord spacing? These questions guide his nights, and each new page represents a microcosm of possibility. At 28, Rusty has no degree, no formal recognition, and no European experience. He has never flown a Spitfire. He has never presented a paper to the Air Ministry. And yet, he is about to imprint his ideas on the very edge of Allied aviation. His strength is not brilliance in isolation, but a combination of obsessive curiosity, hands-on mastery, and the moral courage to challenge the consensus quietly but relentlessly. Rusty is the embodiment of a principle that would become uniquely American during the war. Innovation does not require permission. The world can mock, deride, or ignore an idea. Yet if it is valid, it will find a way forward. And Rusty Carter, working silently in Ohio, pencil in hand, eyes fixed on the spinning horizon of theoretical aerodynamics, is that principle made flesh. By the end of a single night, he will begin to sketch the coaxial contra-rotating propeller that, if applied correctly, could push a Spitfire into realms of speed previously considered impossible. Not through politics, not through rank, not through visibility, but through relentless faith in hands, numbers, and imagination. By 1942, the Allied air effort faced a subtle but brutal enemy, physics itself. Engines were becoming more powerful, superchargers more efficient, fuel formulations more advanced. Yet each extra horsepower encountered a law of diminishing returns. The airframe could only translate so much energy into speed before drag, torque, and turbulence consumed the gains. This invisible ceiling frustrated engineers and pilots alike. The Spitfire, Britain's crowning achievement, was agile, sleek, and fast. Yet it too approached the limits imposed not by design, but by the inefficiency of propeller technology. American engineers observed the same problem in their own aircraft. The Merlin and Allison engines could generate more power, but converting that energy into usable thrust remained the bottleneck. Single, conventional propellers would hit a wall. The airflow stalls at high rotational speeds, tip vortices become destructive, and torque couples introduce uncontrollable tendencies in the airframe. Raising engine power alone could not overcome these fundamental aerodynamic limits. The problem was not in the engine, nor in the pilot, nor in the wing. It was in the disc, the invisible circle of blades at the front of the aircraft. Contra-rotating propellers were known in theory, but the track record was messy. Side-by-side twin-prop configurations failed because the wakes collided, producing chaotic drag and reducing efficiency. Even small misalignments in phase or pitch could produce catastrophic torque effects. In short, the geometry seemed cursed. Every prototype brought destruction or disappointment. American engineers who had attempted twin discs had returned only reports of vibration, mechanical failure, and inexplicable loss of control. The data suggested the idea was impractical. And yet, Rusty Carter saw something the textbooks did not. He had spent years absorbing the patterns of failure. He recognized that the destructive interference was not an obstacle to overcome, but a potential resource to harness. If the front disc generated a controlled disturbance, and the rear disc captured and reoriented that energy, then chaotic airflow could be converted into thrust instead of wasted drag. Torque cancellation and gyroscopic precession could be mitigated if the discs spun in opposite directions, properly phased. The technical challenge was enormous. The aircraft control surfaces were already operating near their authority limits. The airframe could not tolerate large deviations in yaw, pitch, or roll caused by gyroscopic forces. The propellers themselves had to withstand unprecedented centrifugal stresses. Every small miscalculation could destroy the blades, tear the nose assembly apart, or send the aircraft spinning uncontrollably. Yet Rusty persisted, driven by an insight few others could perceive. The secondary problem was cultural and political. Rusty was an American trying to improve a British fighter. Diplomacy, pride, and hierarchy dictated that he should remain silent. The British engineers might dismiss his ideas outright. His peers in Dayton could consider the effort a waste of time. The U.S. Air Corps had no official reason to approve work on foreign aircraft design. In every measurable sense, Rusty was operating without permission, without authority, and without a safety net. But America's industrial culture provided a hidden advantage. Freedom to experiment, even without oversight, was a uniquely American trait. In Ohio, a machinist could take scraps of aluminum, night shifts, and a pencil and attempt what the bureaucracies of Europe would never allow. Failure was a metric, not a punishment. Repetition and iteration were tools for discovery. This environment allowed Rusty to attack the problem obsessively, without regard for convention, authority, or social expectation. And so the problem became Rusty's obsession. He tried side-by-side discs, differential pitch arrangements, and staggered geometries. Each iteration failed. He recorded torque anomalies, flutter, vibration, and destructive resonance. Every failure was analyzed meticulously. The breakthrough came when he shifted focus. The two discs should not cooperate in the conventional sense. Instead, they should be designed to interact constructively through controlled conflict. The front disc creates turbulence. The rear disc mines it for thrust. The chaos is the engine of acceleration. This radical rethinking violated decades of aerodynamic orthodoxy. Textbooks emphasized smooth flow, predictable wake, and uniform lift distribution. Rusty's approach embraced mess, disorder, and constructive interference. It was counterintuitive, almost heretical. But the numbers suggested a path forward. If executed correctly, the twin contra-rotating discs could allow the Spitfire to exceed previously accepted speed limits. A 470 miles per hour piston-powered fighter was no longer theoretical nonsense. It was an achievable target. The stakes were high. Fail and the idea dies quietly, dismissed as another machinist's folly. Succeed, and the method could redefine fighter performance, influence aircraft design on both sides of the Atlantic, and provide the Allies with a speed advantage that might matter in life-or-death engagements. The technical, cultural, and personal challenges coalesced into a single daunting problem: convert raw power into usable speed without creating a disaster in the cockpit. And yet, it was precisely the magnitude of the problem, the impossible nature of the physics, the audacity of challenging orthodoxy, and the freedom allowed by American industrial culture, that set the stage for innovation. The problem was not merely a technical hurdle. It was the crucible that would define Russell Carter's ingenuity, persistence, and moral courage. It was here, amid torque, turbulence, and skepticism, that the seeds of a revolutionary approach to fighter performance were planted. The night in Dayton was silent, save for pencil on paper and the quiet hum of electricity in the shop. Outside, the world was at war. Inside, a single machinist was waging a different kind of battle, against limits, against expectation, and against convention. And in that struggle, the problem that had stymied generations of engineers began to give way to possibility. The most extraordinary thing about Rusty Carter is not the idea itself. It is the way he approaches the idea, the way America itself shaped the environment that allowed him to think this way. By 1942, the United States had become a war laboratory. Factories churned out engines, wings, propellers, and planes at speeds that defied precedent. Midwest machine shops hum with electricity, oil, and the rhythmic clatter of lathes. In these workshops, the rules were simple: the numbers decide. Precision matters. Repetition matters. Ingenuity matters more than credentials. Here, a machinist without a degree could invent, iterate, and test without waiting for permission. Failure was data. Innovation the only currency. Rusty's nights in Dayton exemplify this principle. Every pencil stroke on graph paper, every calculation in the margins, every scrap of aluminum shaped and recut is part of a dialogue between mind and metal. He experiments not because he seeks recognition, but because he cannot imagine doing otherwise. He embodies the American belief that ideas, not hierarchy, drive progress. The twin contra-rotating disc concept is radical, but it is also deeply American. It ignores conventional wisdom. It disobeys orthodoxy. It transforms chaos into a weapon. To outsiders it looks reckless. To Rusty it is rigorous, measurable, and reproducible. The first disc will churn the air. The second will harvest the swirl, converting turbulence into forward thrust. This is the opposite of textbook aerodynamics, but it works on the test bench. Night after night, Rusty and Don, his friend and fellow machinist, iterate. They cut blades from scrap aluminum, adjust pitch and phase, and measure conversion efficiency. Failures come in quick succession. Torque spikes, flutter, broken blades, but each one is recorded, analyzed, and used to refine the next design. Persistence here is more than a virtue. It is a method. And then one night the breakthrough arrives. A subtle shift in phase alignment, a deliberate asymmetry, transforms the behavior of the discs. Efficiency rises. Torque stabilizes. The chaotic wake of the first disc becomes usable power for the second. It is not elegant. It is not finished. It is not even authorized. But it works. And that is enough. America rewards the working prototype, not the promise. Unlike Europe, where bureaucracy can suffocate innovation, Dayton allows Rusty to send his sketches and data to Britain, daring them to consider what the numbers suggest. The act is not boastful. It is defiant, but quietly so. In the margin of one sheet he writes simply, "If it works, use it." That is the creed of American engineering in wartime: freedom to fail, freedom to innovate, and faith that the truth of the machine will prevail. Rusty's work is also a cultural statement. He is American, and America values initiative over pedigree. The British Spitfire, beautiful and refined, represents the old world: craftsmanship, doctrine, hierarchy. Rusty's contribution is industrial, pragmatic, and fearless. It is the new world asserting that speed, efficiency, and raw ingenuity can outpace tradition when the world demands results. The implications extend beyond one prototype. The approach defines how American engineers tackle every wartime problem. Identify a bottleneck, challenge orthodoxy, iterate relentlessly, and never fear failure. Rusty's contra-rotating discs are a microcosm of this ethos. Every test, every adjustment, every minor improvement is proof that America's strength lies not in brute force, but in the freedom it gives its innovators. By the end of the experiment, Rusty's test bench has produced more than data. It has produced confidence. It has demonstrated that a solitary, determined mind, given the tools, space, and permission to explore, can challenge assumptions, break boundaries, and deliver results that reshape the battlefield. And yet, the human element remains. Rusty is exhausted. Don is exhausted. Both understand that the next step, convincing others, translating the benchwork into operational aircraft, will require diplomacy, patience, and careful communication. The idea is fragile. The numbers are promising but not yet definitive. One miscalculation, one misinterpretation by the British engineers, could dismiss the concept entirely. But the American way persists. Iterate, measure, improve. Trust in results over hierarchy. Prioritize the machine, the metal, and the math over politics and ego. In Dayton, that principle has produced a moment that will reverberate across the Atlantic. A single machinist, working nights, has not only challenged conventional wisdom but has provided a pathway to pushing a legendary fighter beyond previously imagined limits. Rusty Carter's story, and the story of his discs, is quintessentially American. It is the story of freedom to innovate, of grit and stubbornness, of the quiet but unstoppable belief that possibility exists wherever you are willing to look for it. In the context of 1942, it is a story of how one man in one small shop can shape the course of aviation history without permission, without accolades and without fanfare, simply by embracing the American ethos of ingenuity, persistence, and fearless experimentation. The breakthrough in Dayton was not a headline. There were no ribbons, no fanfare, no press releases. It was simply a spindle spinning at the right RPM, blades cutting through aluminum, and numbers that finally obeyed expectation. But for Rusty Carter, and for the story of the twin contra-rotating propeller, this was the moment when possibility became reality. After weeks of failures and incremental adjustments, Rusty and Don finally documented a configuration that worked reliably in the test rig. The torque anomaly vanished. The second disc harvested energy rather than fighting the first. Conversion efficiency increased measurably. It was a modest gain, but in the world of aerodynamics, a single percentage point can change the destiny of an aircraft. With proof of concept in hand, Rusty faced the next challenge: communication. He was a machinist. His authority ended at Dayton's workshop door. If he wanted the idea to matter, it had to leave Ohio. He chose to reach across the Atlantic, targeting the British engineers responsible for Spitfire performance. This was not simple. International correspondence on technical matters was rare, formal, and slow. Mistakes or misunderstandings could dismiss the work before it even arrived. Yet Rusty's approach was characteristically plain-spoken and precise. He enclosed his drawings, test data, and a single sentence: "If it works, use it." Weeks later, a reply arrived. The British engineer, intrigued, acknowledged the possibility. It was cautious, respectful, but not enthusiastic. No promises were made. Rusty's design would have to survive rigorous scrutiny, wind tunnel tests, and calculations before anyone risked applying it to an operational aircraft. Meanwhile, in Dayton, Rusty pushed further. He refined the blade angles, experimented with pitch distribution, and optimized the stacking distance between discs. Every night brought incremental improvements. Every success confirmed the theory, every failure taught something new. His methodology was relentless but methodical. Test, record, analyze, iterate. This was the American way in action: independent, empirical, fearless, and effective. The turning point was not a single calculation, nor a single letter. It was the convergence of persistence, proof, and international attention. The concept had moved beyond an idea on paper. It had demonstrated viability in practice and had gained the cautious interest of engineers who could transform it into a weapon of war. Rusty's solitary workbench became the seed from which international development could grow. At this stage, the risks were enormous. A miscalculation could destroy the test rig, injure personnel, or render the design unusable. Yet Rusty's experiments remained disciplined. He understood both the potential and the danger. His obsession with precision, combined with creative audacity, allowed him to navigate the fine line between genius and disaster. The result of this turning point was clear. The stupid twin-propeller design had evolved from a personal theory to a recognized concept with practical merit. It had survived scrutiny, demonstrated measurable gains, and captured the attention of those capable of implementing it on operational aircraft. This moment marks the shift in the narrative. Rusty Carter was no longer merely a machinist tinkering in Ohio. He had become a catalyst, a bridge between American ingenuity and the broader Allied war effort. His idea was poised to influence aircraft design, potentially altering the dynamics of air combat and the performance of fighters that would engage the Axis powers in the years to come. The turning point is both technical and symbolic. Technically, it validated the twin contra-rotating concept and established the parameters for its application. Symbolically, it reinforced the unique American ability to innovate without hierarchy, to experiment without fear of failure, and to trust empirical results above all else. Rusty's journey demonstrates how courage, patience, and relentless focus on measurable truth can turn a solitary idea into a force capable of shaping history. The first practical applications of Rusty Carter's twin contra-rotating propeller were subtle, almost invisible at first. No battles were won overnight because of a single Ohio machinist's sketches. Yet the ripple effects across Allied aviation were immediate and measurable. British engineers who examined the drawings began to incorporate the principles into wind tunnel tests, adjusting blade geometry, pitch, and phase. Spitfires tested with the modified configuration demonstrated incremental improvements in speed, stability, and torque control. Small at first, but enough to convince skeptics that the idea had merit. In a world at war, small improvements can become decisive. The Spitfire's enhanced performance allowed pilots to engage enemy aircraft with a margin previously unavailable, giving them extra seconds to evade, position, or escape. A few knots of additional speed could mean the difference between life and death. When you multiply these gains across dozens of squadrons operating in Europe, the cumulative effect becomes profound. Rusty's concept had introduced a hidden edge into the Allied toolkit, invisible to the enemy, difficult to quantify in conventional terms, yet real on the battlefield. American industry also benefited. The principles Rusty developed inspired domestic designs, influencing prototypes in the U.S. that incorporated contra-rotating discs or coaxial propellers. Engineers adapted the lessons of torque cancellation, energy recapture, and phase alignment to aircraft already in production, pushing the performance envelope of fighters and reconnaissance planes. By blending practicality with daring experimentation, the concept spread quietly but decisively across both sides of the Atlantic. Pilots, though unaware of the individual behind the innovation, felt the effect in the air. The aircraft responded more predictably at high power settings. Spins and torque-induced accidents decreased. Speed potential increased without sacrificing maneuverability. Each test flight, each combat sortie, carried with it the invisible fingerprint of Rusty Carter's nights in Dayton, a testament to the power of relentless, methodical ingenuity. Beyond the technical, the story underscores a cultural impact. Rusty's work became a blueprint for how American engineers approached challenges. The process of experiment, iteration, and data-driven refinement, even in the face of skepticism, became a model. His approach validated the idea that innovation does not require fame, degrees, or bureaucratic approval. Instead, it requires persistence, courage, and meticulous attention to empirical truth. Strategically, the gains in aircraft performance contributed to a broader pattern in the war effort. Allied air superiority increasingly relied on small, cumulative advantages. Faster, more stable fighters meant more effective escort missions for bombers, reduced losses, and greater operational flexibility. While no single pilot could attribute survival to Rusty's discs, the principle of invisible innovation became a recurring motif in the Allied campaign. By the end of 1943, the twin contra-rotating principle had moved beyond Dayton, beyond sketches, beyond wind tunnels. It had entered the bloodstream of practical aircraft development. It had altered the trajectory of fighter design in subtle but irreversible ways, proving that innovation could come from the most unexpected places. From a quiet machine shop in Ohio, from a machinist who refused to accept conventional limits. And so, the impact of Rusty Carter's work is measured not just in knots of speed or reduced torque, but in the demonstration that America's strength in wartime innovation lies in empowering individuals to think freely, experiment boldly, and persist relentlessly. The world could measure airplanes in engines, wings, and guns. America measured them in ideas. Rusty Carter never sought fame. His name rarely appeared in official records and certainly not in headlines. Yet his influence endured, quietly, invisibly, like the thrust of the propellers he designed. The twin contra-rotating concept became a template for high-performance fighters and experimental aircraft in both Britain and the United States. Engineers who followed in his wake applied the principles to new designs, pushing speeds and performance envelopes far beyond what previous generations believed possible. The legacy is also cultural. Rusty exemplifies the uniquely American ethos of wartime innovation, the freedom to tinker, the courage to defy orthodoxy, and the belief that practical genius can come from anywhere. In Dayton, in a modest workshop, he proved that one man with determination and insight can bend the limits of physics and design. His work demonstrated that ideas, not just machines, win wars. Decades later, military historians and aviation enthusiasts would trace the evolution of high-speed piston aircraft back to small breakthroughs like Rusty's. Contra-rotating and coaxial propellers became part of a lineage that informed post-war fighter design, jet transition strategies, and the broader philosophy of performance engineering. In classrooms, museums, and archives, his diagrams and notes are studied as examples of inventive thinking, the intersection of empirical rigor and imaginative audacity. Perhaps the most enduring lesson is human. Rusty's story reminds us that innovation thrives where freedom, curiosity, and persistence meet. America's victories in World War II were won not just with engines and guns, but with minds unafraid to challenge the impossible. Every advance, every design improvement, every small edge in performance carries the fingerprints of individuals like Carter, who pursued the improbable with quiet determination. Even today the principle resonates. Engineers, inventors, and problem solvers in every field can draw inspiration from the story of a machinist in Ohio who refused to accept limits, who embraced failure as a teacher, and who understood that a single idea pursued relentlessly could ripple across continents and shape history. Rusty Carter may remain unknown to the public. His nights spent at a drafting table might never have been recognized outside of technical circles. Yet the impact of his work endures, embedded in every high-performance aircraft that benefited from the twin contra-rotating concept. His legacy is a testament to American ingenuity, persistence, and the quiet power of one determined mind. The war moved on, larger battles claimed headlines, and the names of generals and aces filled the newspapers. Yet behind the front lines, in workshops, factories, and drafting rooms, men like Rusty Carter quietly reshaped the tools of victory. His work on the twin contra-rotating propeller did not make him famous. It did not bring medals. But it changed what was possible. The Spitfires that benefited from his insights were faster, more responsive, more deadly, a subtle advantage that mattered in dogfights, escort missions, and strategic operations. The gains were invisible to most, unheralded, yet undeniable. Every additional knot of speed, every ounce of reduced torque, every increment in efficiency carried the echo of Rusty's nights of work, the sketches, the calculations, the endless iteration. Rusty's story is a quiet reminder that America wins wars not solely with weapons, but with ideas. Freedom to experiment, courage to challenge orthodoxy, and persistence in the face of ridicule, these are the forces that tip the balance. The machines of war are important, but the minds behind them are decisive. And so, the story of this stupid twin-propeller design is more than a tale of innovation. It is a testament to the power of individual ingenuity, the value of quiet persistence, and the profound impact one determined mind can have on history. In every spool of film, every black-and-white photograph, every technical drawing that survives, the legacy of Rusty Carter whispers, "Progress favors the bold, the curious, and the relentless." Years later, long after the war ended, Rusty Carter returned to a quieter life. The world had moved on, the Spitfires had flown their last combat sorties, and jet engines were already redefining speed and performance. Yet, the imprint of his work remained, a subtle, invisible thread woven into the fabric of Allied aviation history. Historians would later trace improvements in fighter performance back to innovations like Carter's twin contra-rotating design. Engineers cited his principles when designing post-war experimental aircraft. The lessons of torque management, energy recapture, and bold iteration continued to inform aerospace development for decades. And though his name was seldom spoken outside technical circles, the impact of his thinking endured. Rusty himself never sought recognition. For him, the measure of success was not applause or medals, but the quiet validation of seeing an idea survive rigorous scrutiny and then influence outcomes beyond his small workshop. He had proven that an uncredentialed machinist, armed with curiosity, persistence, and the freedom to fail, could contribute meaningfully to the course of history. Ultimately, the story of Rusty Carter and his stupid twin-propeller design is a lesson in the power of ideas. Wars may be fought with weapons, but they are won with innovation. America's edge lay not only in its factories or fleets, but in the minds it allowed to think freely, challenge convention, and pursue the improbable. Carter's legacy is a reminder that progress does not always come from the famous or the celebrated. Often, it comes from those quietly determined to see what others say is impossible. And as the last pages of his notebooks quietly attest, the greatest victories often belong to the thinkers, the tinkerers, the relentless, the ones who look at the impossible and simply begin to draw.